So now we will talk about quadratic optimization problems. So these are also called QP. So the problem statement is to minimize a quadratic function that is also a convex function. Quadratic optimization problems are convex optimization problem where the objective function is quadratic and subjected to inequalities. Those are affine functions. And also the equalities are affine functions. Okay, here G belongs to R of n cross n, and in A belongs to R of P cross n. Also, here P is positive semi-definite. So we can see that the feasible set will be like a polyhedron if we geometric interpretation. Geometrically, it will be like a the feasible set P is still a polyhedron. However, the dashed line represented by the objective functions, the level curves of the objective function, that will be quadratic. We saw a similar diagram for the linear program. There, those dashed curves were of a linear form. So there is this difference, and let's suppose x star is the optimization point, the optimal value x star, and this is normal to the slope at x star. So this is kind of the geometric interpretation of quadratic optimization problem. We can observe here that if P is equals to 0, then it is a linear program. If this is 0, then this won't exist, and this is like a linear program. Okay, and a more general case will be of quadratically constrained quadratic program. Here we minimize the objective function which is quadratic. Subjected to the inequalities. Here the inequalities were affine, but here the inequalities are also of the quadratic form. For I equals to 1 to m and ax equals to b. The equalities are still affine. And PIs are also positive semi-definite. So this is more general. If we can see that if we take all the PIs equals to 0, it will lead us to this form, again quadratic program. So the quadratic program is a special case of quadratically constrained quadratic program, and linear programs is a special case of quadratic programs where p is equals to 0. We will now look at some examples. Distance between polyhedra. We are talking about Euclidean distances here. So the polyhedras are and P2 and both of them are defined in Rn. So we have to minimize the distance between the polyhedras. So distance of P1 and P2 is the infimum of the distance between x1. x1 is the point optimal x1 for P1 and x2 is for P2. The optimal point that satisfies the minimum distance between these two polyhedras. So the geometrically if we try to look at this, so this is P1, this is P2, and let's suppose this is, so this is not necessary that those will be at certain point. There can be these points also, that is closures. I just draw it like this. So there is x1 and there is x2. So this kind of geometric interpolation. If p1 and we can see if p1 and p2 intersects, then the distance is 0, and it is feasible if and only if one of the polyhedron is, I mean, it's if both of them are exist or not empty. If it's infeasible if one of them is empty. Right. So the problem statement will go like, so we have to minimize or infimize this these 2 points, optimal points. So the problem statement we have to do is subject to but we can see that we can change it to a quadratic program form by squaring the objective function. So it will be like right. So this is the quadratic program that will minimize the distance between the polyhedra P1 and P2. We can solve this to find the optimal x1 and x2. Another such example can be linear program with random cost. So we look at a linear program where we have to minimize the cost function subject to the other affine inequalities. However, the difference here is that the cost function here is random, that is C is random. So when C is random, two things comes into picture is the expectation and the variance of C. So we say that the mean is C. We say this is the mean, and covariance of C is the expectation of C minus expectation of C times the transpose of it. Will be we are using this notation, and we keep the other parameters deterministic. So So the expectation, we say that the expectation of this is equals to C transpose Tx. So this is the expectation, and similarly the variance of C transpose X is, because the other parameters are also deterministic, what we really do with it is we create a value that will take care of, that will be kind of a trade-off between the expected value of C and the variance. So we modify this the linear program where the cost is random to a function that is called risk sensitive cost, risk sensitive cost, and where the gamma value, which is greater than equal to 0, is called risk aversion parameter. So if gamma is equal to 0, then we are not worried about the variance. Exactly, no matter how much the cost vary from the expected value, we are not worried about. We are only trying to minimize the cost function. However, the gamma value we choose, if it's greater than 0, that means we are trying to have a trade-off between the expected value and the variance of the cost function. By this I mean, like, if the even if the value is higher, we are, even if the cost function, this we are trying to minimize this right here. So what we are saying here, that if even if the value of the expected value of cost function is higher, we are willing to take that up as long as the variance value of it is low. So if the expected value is like this and the variance is quite high, we are not picking such a value. However, if it is a bit higher than the previous one, but the uh, variance is low, so we are willing to take this one over this. Okay, so yes, so now we modify, so our modified function will be of however, we can also write this as using these two values. So our modified cost function, taking in the variance and expectations, will be to minimize the quadratic program. This will be the objective will be a quadratic function, and the rest will remain the same. So now this is a quadratic program. So now we go to the next topic, that is geometric programming. Monomials and polynomials. A function from Rn to R and having a domain, a positive domain, defined as is called monomial function. Where AIs are real and CI and C is positive. Monomials are closed under multiplication and division. And another function f of x, that is the summation from k equals to 1 to k of such monomials and this function is also from R into R is called, and ck is also greater, is called polynomial function. And it is closed under multiplication, division and addition. So this is a polynomial function with k terms. If we are adding another terms, it will be k plus 1 term polynomial function. Even if we multiply monomial with a polynomial function, then also it will be a polynomial function. Now we come to the definition of geometric programming. Here we have to minimize the objective function f naught of x subject to f i's of x lesser than equal to 1 and hi of x equals to 1 equal to 1 2. Okay, and here the f0, f1, fm are polynomial and h1, h2, hp are monomials. This is called geometric program, GP. Domain is again the positive Rn, where x greater than 0 is implicit, because this is implicit. Here we can see that if any of them are lesser than 0, then we cannot define this kind of a product. Otherwise it might not always be real. Right. And what we told before, that monomials are closed under this kind of multiplication and divisions of them, and polynomials are closed under the multiplication, division and addition. This can help in handling many different equalities and inequality conditions. So we see extension of GP. One of the case can be f of x, which is a polynomial, is lesser than equal to h of x, which is a monomial. This we can see that is itself a polynomial of this form, because is polynomial. Similarly, another case can be, this is another special case. A we can also represent as any product of two monomials, and we can take it to the left hand side and say that it is still a polynomial. Another can be the equality of monomials. This kind of what we are trying to do is we have to achieve to this kind of equalities and inequalities as the constraints. So this we can write as which is again monomial, because monomials are closed under multiplication and division. One simple example we can see here is, suppose we have to minimize, just in an example, we have to minimize x by y subject to x less than equal to 3 and x square plus 3y by z less than equal to root of y. And x by y is equal to z square. Right. So using the previous three, we can see here that x by y we can write as x y inverse this we can break into parts, x which is greater than equal to 2 and x which is lesser than equal to 3, that is 2x inverse less than equal to 1 and 1 by 3x less than equal to 1. This comes from this kind of a form. And x square plus 3y by z less than equal to root of y. You can bring it to one side and say that x square y 1 by 2 minus 1 by 2 plus 3 times y 1 by 2 z inverse and we can write this. So this is a combination of monomials, we can see. So this is a monomial, these are polynomials, this is a total is a polynomial, and we are seeing that if we think of this case, this is arrived at. So this is from this. So we can modify our the objective function and the constraints as minimize, subject to 2x equals this, this, so another thing is that these are polynomials, and also this is a polynomial with k equals to 1. So this is our GP. Now we see geometric program in convex form. So note that this in generally the geometric programs are not convex optimization programs, so we have to transform them by some change of variables of the objective and the constraint functions into a convex program. So there are xi's in the polynomial and monomial functions. So we take logarithms of these. So we take the yi's as the logarithms of the xi's, such that we replace the xi's by e of yi. So given f is a monomial, we write the fx as . Now we replace all the xi's by e power yi's. So now the f of x is a function of e power yi's y1. This is just manipulation of the variables. Okay, and we can also write c as log of some b, log of c as b. So this will mean c is equal to e power b. So we replace the c in here. Okay, so this we can write like exponential of a affine function. Similarly, for this fx is for monomials, and for polynomials this will be like a combination of the summation of the exponents of affine. So where ck is e power b cancel. This is like a summation of sum of exponents of affine functions. So we can write like this in terms of the new variables. We have not changed anything as of now. Okay. Subject to the inequality and the equality constraints. We're just replacing all those we are just replacing these by our new variable y. Okay, yeah. Right. From I equals to 1 to, yeah. Now this is same as the the original geometric program. Now we transform the objective and the constraint functions by taking the logarithms of uh, taking the logs of all these functions. So logarithm of objective and constraint functions, minimize so what we are doing here is taking the logarithms of the objective function subject to if I tilde of y logarithm of the constraint functions and the logarithm of this will be like gi y plus hi and log of 1 is 0. So right now all the fi's are convex. Those are the log of these the objective and the constraint functions, and hi are affine. So it is indeed a convex optimization problem. So this is called convex, right, form of geometric program, and the previous one was polynomial form of geometric program. And another observation we can see here is that if all the polynomials are actually monomials in the form of monomials, if all the polynomials are in the form of, so this is a polynomial because it is a summation of all the monomials, and the constraint inequality is also a polynomial. So if it is not a summation, that is either k is equals to 1 or it is actually a monomial, so then we can see that this is like an affine function, right? So then it will be actually a extension of linear program. So if all the polynomial objective and constraint functions are monomials, then convex form of GP reduces to L. And next we see one example of the GP problem. That is design of cantilever beam. So this is kind of a beam with n segments, starting from segment n minus 1 and going till segment 1. It is uniformly placed and it has the length of these lengths are same, but there are the widths also, so it's like this. Right. So these widths are WIs and these heights are HIs. So the problem is that there is a load we apply a load here, and this downward load causes a deflection in this beam, and this deflections these deflections are caused and these deflections are uniformly these deflections are very small, and there is a concept of there comes a concept of Young's modulus E, because the material is linearly elastic, and so the objective here is to minimize the volume of the beams. And which is proportional to Wn Hn. So we have to minimize this the total volume of the beam, which is proportional to its weights, and there are some design constraints. So this is a minimization problem, as you can see. So but there are some design constraints we have to take care of. That is, there are lower and upper bounds on the widths and the heights of the beams. So there are these kind of lower and upper bounds. For I from 1 to n. Also there is the bound on the aspect ratios, so it has to follow some aspect ratios, and there is a bound on the aspect ratios S. Also there are some limits on the arrival stress in the material and the vertical deflection at the end of the beam. So if we look at the stress factor, so the maximum stress we denote by sigma max. So this will be maximum stress will be lesser than sigma max. And so this value is actually segment wise stress, the maximum stress in segment I. So to ensure that the stress is does not exceed the maximum allowable value of sigma max anywhere in the beam. So this is why we set a maximum of this, and this value is actually equal to sigma I, that is the segment wise maximum stress allowable. And this segment wise stress anywhere in the entire cantilever beam should not be greater than sigma max that we have. This is one of the constraint. Another constraint is which I was saying is that of a vertical deflection at the end of the beam. So the vertical deflection y1 should be lesser than maximum value, vertical deflection. So I mean, to find this y1 we have to find the value of y1, that is the vertical deflection at the end of the beam. We start with an equation vi, which is the slope quantities, these are the slope quantities, and wi's are the yi's are the deflections for each segment. So vi is equals to this. So E is the so F is the force we are applying, and E is the Young modulus. So this is kind of a recursive value. Also yi's are recursive with this formula. So what we can see here is that so, and also one thing we have to note is that v of n plus 1 is equal to y of n plus 1 equals to 0, which is polynomial. 0 is a polynomial. So y of n plus 1 is a polynomial, plus this is a monomial in wi and hi's, which are the variables, and vi or v of n is a polynomial which is the addition of a monomial and a polynomial. Addition of monomial and a polynomial is a polynomial itself. Then once we get the v of n, we can get v of n minus 1 similarly by putting v of n here, and in a recursive manner we will achieve v of 1. Similarly, y of n will be a polynomial addition of two polynomial and one monomial, and we will get y of n. Now once we get y of n, we will put here the y of n and the v of n, and this will give us y of n minus 1. In a recursive manner we will get the y of 1, and so we are using y of 1, we are using v of 2 to get y of 1. So the problem is changed into a kind of a geometric problem, this entire problem with this objective function and other minimizing constraints like this, 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 and this. So this can be said as this only, right? So another thing to note was that these are all polynomials, so the inequality is a polynomial. So that's why I was stressing on this part, because we need to write it in a GP form, so we have to have the inequality constraint as polynomials. So the function, the program, the GP will be minimize the subjected to we can further means drop these inequalities into two separate parts that we can do. HIs the aspect ratios the maximum stress this value is for each segment the maximum stress. So we have to check that for each segment, for every segment this stays below the sigma max value, and then the deflection of the last y1, since right I'm not writing this function, this will come from recursively solving these two. So this is a GP in with variables wi and hi. These are the variables. We have to minimize this. So this is a GP example of GP. Thank you.